The M&M Mars Corporation used to publish the proportion they produced of each type of M&M. For example, each batch was 13% red, 20% orange, etc. Now, they don't do this anymore, so these numbers might no longer be accurate. But suppose we wanted to test this, right? We could go out and buy large bags of M&Ms, count up all of the colors, and convert them to percentages. And we'd end up with something like this, right? From here, we could do 6 separate tests, one for each pair of proportions. But what if we get mixed results? Maybe we get 2 strong rejections, that is, results with very small p-values, but 4 kind of weak don't rejects. Now what should we conclude? How are these things all going to balance out? Right, well, the method for resolving this, that is combining all of these results into a single conclusion, is called a goodness of fit test. Now, before we start digging into the calculations, I want to make something clear that I implied in the title on the first page. The variable we're working with here is color, which is non-numeric. Specifically, it represents categorical data. This kind of test is going to represent a significant change for us. Right? For the first time, we're thinking about how to do a test working with variables that are non-numeric. Now, to do this, we can't work with percentages. We need the actual counts of each color. And that's easy enough when we're working with the sample. Just record the numbers and don't do the extra step to convert to a percentage. And that's how I've rewritten the numbers in the first column and updated the heading here with an O for observed. Right now, the other column is going to have the expected values. Right, that is the number of values we expected to get from a sample of the same size based on what we were told to expect. Now, if you total all of the sample values, you'll see that the sample size was 50. So the E values will just be 13% of 50, which is 6.5, 20% of 50, which is 10, etc. These are the numbers that we're actually going to use to calculate our test statistic. So I've got all the key elements of our test here. Starting on the left side, the O and E values are the observed and expected values. Those are the frequency counts. The O values come from the sample, and the E values are calculated based on the sample size and the expected percentage frequencies. K is the number of categories. That would be the number of colors in my M&M's example. And N is the sample size, just like it always is. Now, we also have a few minimum requirements here. Right? We need randomly selected data, and the data has to be frequency counts. And finally, the expected frequency for each category has to be at least 5. Now, that only applies to the expected values. It's okay for the observed or sample values to be lower than that. All right, so with all of those expectations, our test statistic is a chi-squared value that's found by subtracting the matched observed and expected values, squaring them, dividing by the expected value, and then adding up the results. Now, so far, this has all been pretty standard, right? We've got some variables, some requirements, and a formula for the test statistic. The null and alternative hypotheses, on the other hand, are more interesting. If you look back over all the tests that we've done so far, the null and alternative hypotheses have always been either an equation or an inequality talking about a population parameter. Well, we can't do this here because we're working, again, for the first time in quite a while, with categorical or non-numeric numeric data. So our two hypotheses here are just English statements, plain English sentences about what our expectation is. Right, so now we've got all of the pieces in place. We know our requirements. We know what our test statistic is going to be. So we're ready to go ahead and look at some specific examples.